Hi, so the first thing we need to do in this problem is to find the moment of inertia of this solid disk. And the equation for moment of inertia of a solid disk is I disk is equal to half mr squared, where m is the mass and r is the radius. We have the radius of the disk, it's half the diameter, 125 millimeters, but we need to find the mass. In order to do that, I'm going to use the following equation. M equals rho V, where rho is the density of the material, which we have in the question, and V is the volume. In order to find the volume, we must find the area of the disk and multiply it by the height. V equals pi r squared h. So V is equal to pi r squared, which is the area of the circle, multiplied by the height. So these three equations will give us the inertia of the disk, starting with the volume. Now, the volume is equal to pi multiplied by the radius. The radius is 125 mil. We need it in meters, not millimeters. So it's going to be 125 divided by 1,000. That's the radius. Then we square the radius, multiply by the height, which is 50, again divide by 1,000 in order to transfer it into meters. So this gives us a volume of 2.45 times 10 to the minus 3 meters cubed. That's the volume of the solid disk. Now substituting this volume into the mass equation, we have M equals the density of the material is equal to 1270 kilogram meters cubed. 1270 kilogram meters cubed, all multiplied by 2.4 times 10 to the minus 3. Now, this gives you a mass of 3.1 kilograms, which is realistic, it's quite a small disk. Finally, in order to find the inertia, we simply substitute into this equation here. Equals half multiplied by the mass multiplied by the radius squared. Don't forget the radius is 125 divided by 1,000, all squared. This gives us a inertia value of 0.02 kilogram meter squared. So part 2 of the question basically asks us to find the energy transferred from the flywheel to the car. Now the initial speed of the flywheel was 40,000 RPM. As the boost button is pressed, energy is taken from the flywheel and transferred to the wheels of the car. And that has resulted in the speed of the flywheel dropping as it has less kinetic energy. It drops to 25,000 RPM. So first thing we're going to do is we need to transfer this RPM into radians per second. The way to do that is simply omega is equal to take your RPM, multiply it by 2 pi over 60. That gives you rad per second. We can do the same thing here. We can say omega is equal to 25,000 in this case, multiplied by 2 pi over 60 rad per second. So that's the two angular speeds of the flywheel at each given moment in time. Now let's look at the question. We need to find the energy transferred. The energy transferred will be the energy lost. That lost energy, if there's no frictional or heat losses, that energy lost is actually the energy transferred to the wheels of the car. So it's not actually lost, it's transferred. It's the difference in energy. And rotational kinetic energy is defined as KE is equal to half I omega squared. So let's find the kinetic energy of the flywheel when it was rotating at 40,000 RPM. We have half multiplied by 0.02, which was our inertia, multiplied by the angular speed, which is going to be 8,000 over 6 pi. I've just simplified, don't forget the squared, I've just simplified the omega above. The same thing we do with the flywheel when it's spinning at 25,000 RPM. We have half multiplied by 0.02, the inertia does not change. Now this is going to be 5,000 divided by 6 pi, all squared. Don't forget the squared. Now, the kinetic energy before is equal to 175459.6 joules. And the kinetic energy after is equal to 68538.9 joules. So the energy transferred is the change in kinetic energy, which is equal to omega initial, omega naught, minus omega 1, because initially you had higher speed. Subtract these two values from one another, so this minus this gives you a value of 106,920.7. That's 106,920.7 joules. So approximately 106 kilojoules of energy transferred to the car. Now the next part asks us for average power. And power is energy divided by time. The reason it's average is because it means the torque is constant throughout. So we take our energy value that we found in the previous question and we divide it by the time, which in this case is 8 seconds. So we find that the power is 13,365 watts, which is approximately equal to 13 kilowatts of power transferred from the flywheel to the wheels of the car. So the next part of the question is asking us to calculate the decelerating torque on the flywheel. So the equation we're going to use is sum of torques equals I alpha. Now we have the inertia, we don't have the angular acceleration. We can find it, however, by using the constant acceleration equation. V equals U plus AT, that's the rotational version. We're looking for angular acceleration, which is equal to change in speed divided by time. Now let's plug in our values. So alpha is equal to the final speed, which is 25,000 RPM, minus the initial speed, which is 40,000 RPM. Don't forget to multiply by 2 pi over 60 to change it to radian per second, all divided by the change in time, which is 8 seconds. This gives us an angular acceleration of minus 196.34 rad per second squared, which makes sense. You're changing 15,000 RPM in 8 seconds. It's quite a big change in speed, so it requires a relatively high acceleration. Now we go back to the torque equation and we say torque is equal to I alpha, which is equal to the inertia, which is 0.02, multiplied by this value of angular acceleration, which we found. This gives us a torque value of minus 3.92 Newton meter. Now, the final part wants us to find the number of revolutions the flywheel completes in 8 seconds. To find number of revolutions, you must first find the angle by which has been rotated, the total angle. So to do that, I'm going to use another constant acceleration equation. Theta equals omega naught t plus half alpha t squared. Now, we have our initial speed, which is 40,000 RPM, again times 2 pi over 60, which we said previously is 8,000 pi over 6, simplified version, multiplied by 8 seconds, plus half, multiplied by our alpha, minus 196.34, all multiplied by 8 squared, which is 64. Theta is equal to 27227.5. 0.5. That's radians. That's the total angle that it's rotated by. Now, to find how many revolutions it makes, you simply divide what you found here by 2 pi. So in this case, divide your theta by 2 pi. Dividing it will give you 4333.3 revolutions made in those 8 seconds.